I'm Nick Butler. I'm a junior physics major.
I'm David Aguillard. I'm a senior physics major.
This semester we were working in Dr. Martsberger's lab, measuring fractal dimensions and signals from electroencephalogram, or EEG signals. So before we get started, just some background on kind of like the size and the scope of the study. We want to thank Dr. Simats for letting us join in and kind of piggyback off their research. All of our data was collected along with Hunter and Drummond from their study. So we had 79 total subjects that ran through our experiment, and we got about 68 successful runs from which we could use their data. And that came out to about 100 gigabytes of just raw EEG data, which we'll get to in a minute, basically just voltage signals over time. So it was a huge amount of data, so kind of the computation we've been doing has been really intensive and time intensive and taken a lot of work.
So the outline of the experiment, we would place, can I get that? No, that. We placed an EEG cap on our subjects' heads. It had 32 electrodes, and we placed them in one of two groups. Group 1 was shown 9 segments of images. In between each, they would get a memory test based on the images. So in each of these segments were a different theme. So we had negative themes, which was like a wound or something. Kind of get a response out of that. Neutral, which would be like a lamp, and then category, which would be 21 images of a certain category. Group 2 were also shown 9 segments of images with memory tests in between. But they would get a randomized selection of negative, neutral, and category. It'd be 7 of each though. So, and then yeah, the memory test is based off those images. And then the EEG data was recorded throughout these segments, and that's what we've been working with.
Yeah, so this is pretty much a picture of what the EEG data looks like. What it is we place a cap. If you've seen anyone wearing like the funny cap with all the wires coming out, and what it does is measure the voltages across the brain. As many of you probably know, signals are conducted throughout the body as electrical signals. So this EEG cap is capturing those changes in voltage and kind of giving us a picture of the activity that's going on in the brain. So you can see here, these are the readings we're getting. Each of these lines, you can see is coded to a different electrode. So for example, like P4 or O2, those all correspond to a certain location on the brain. So we can see at each location, corresponding to the different electrodes, what the voltage is doing. We actually have a picture of the map that we used. So you can see at the top of the screen, it corresponds with the back of the head, and down here is on the front of the head. So we're basically able to take those readings and understand what's happening at every specific location.
So now we're going to talk about fractal dimension. Now in the EEG data, we're looking for complexity basically, and one way to measure that is with this thing called the fractal dimension. So the best way to describe the fractal dimension in terms of EEG, I think, is with this definition, which is mathematicians. A fractal curve has the property that each part can be considered a reduced scale image of the whole. So if this is EEG data and we take a little piece of it, we blow it up, we expect to see something that looks similar to the whole thing. And if we take another little segment of it and blow it up, we expect to see more complexity reflective of the previous image. And a perfect fractal would keep doing that indefinitely.
Another useful way to think about fractal dimension, it's still the same idea, just kind of a different way of approaching it, is the classic coastline example, which is where if you imagine you wanted to measure the perimeter of the coast of Great Britain, the size of a ruler you choose, like this for example, would have a big impact on what you measure, because you can see it's so complex and there's so many little like nooks and crannies that the ruler misses out. So as we reduce our ruler size, we can more accurately capture those and get a better measurement. So basically, the complexity changes the effect that the ruler size has. So something more complex, like Great Britain, which has such a complex coastline, as you change the ruler size and get smaller and more precise, it's going to have a much bigger impact than something like, usually the classic example is the coast of South Africa. It's much more smooth, so as you change your ruler size, it's going to have less of an impact. So in regards to EEG data, we can look and see if we try to measure the length of these in little segments, the length that we choose to break the segments into, or our ruler per se, is going to have a big impact. So we can kind of use that as a measure of how complex these signals are, is how our measurement, how the scale of our measurement affects the result we get. And you can kind of see, just looking at these, what different EEG signals look like in different mental states with different levels of brain activity. And you can kind of start to get an idea that based on the level of activity, we're going to find different things. There have been studies to back this up as well. For example, patients with their eyes open have higher fractal dimensions recorded. So there's definitely a link that has been established between these fractals from the signal and brain activity.
So the complexity or the fractal dimension of brain activity can also tell you something about a person's health. So for example, Alzheimer's patients have a lower fractal dimension than healthy subjects, and people with depression actually have a higher fractal dimension than people without depression.
Yeah, so basically the purpose of the experiment was we collected all of this EEG voltage data, and we had participants performing the memory test. So we wanted to take all this data and look for a link between the fractalness of the voltage signals coming from the brain and the subject's memory.
So to do this, we use something called the Aguillard method. And we're going to pretend that all our thousands of EEG data points are 8 data points total. And our series, so this is B, this is like the voltage you read, and S equals N, so we get observations. So we're going to pick a ruler length of 2, and we're going to take all these every 2, pull them down, and measure the length based on this. So this one to this one, this one to this one, this one to this one. This is our first length. And then we step down, or step up, and get the next, like now the odd numbers, and we find out like between this, 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 and this, and these are going to be different. We're going to average them, and the average is going to be proportional to K, which is our ruler length, to the negative D, where D is our fractal dimension. And we have to do that for ruler sizes going from 1 up to, we did 58. So that process is repeated, and it's actually the slope of, it's kind of more complicated than I said. But regardless, you keep doing that, and this is and we have like gigabytes and gigabytes of data, and this process takes like, if you run it on one computer, it'll take like 2 weeks to go through one data file. So the point is that it's a very complex process, but we saw that the Aguillard method is a recursive way of examining data with a fixed ruler length. We must repeat that. Before we calculate the fractal dimension, we must determine the optimal choice of K-max, and that was kind of one of the biggest cruxes of our research project. It took a while because we had to run different K-maxes and like look at it and see what we wanted. So there's no textbook way to do it. So we did it like this. We calculated fractal dimension versus the maximum ruler length to run through. For each person, we have group 1 and group 2, so group 1 is blue, 2 is opposite of that. And we found a place where there's the biggest spread in the data. And we based this method on another paper that they did on rats. So you found the biggest spread, and you can see this spread here. As you run up K-max, you get this spread, it increases, it levels off here, and then it goes back down. So this is K equals 58, that's what we picked, and that's what we're going with. And then we could do the actual analysis of the data.
So beginning to kind of look at the results that we've started to get, the first thing we did was try to create a visual representation just to give us an idea and something that's really clear to see. So we created these heat maps. You can see, looking at the map of the electrode placements, that we mapped that over. So we have at each location color-coded the fractal dimension that we recorded as an average over the whole time series. So you can kind of see someone with a heat map like this would have much lower fractal dimensions that we measured over the full time period versus someone with a lot more bright gold colors at the top of the scale, showing that they had more fractal activity.
So we actually just came out with this because we picked K-Max not too long ago, and I've been trying to kind of comb through the data and put things together differently. We found that in the people that viewed negative images, there's a medium correlation between fractal dimension during the test and memory performance afterwards. With a linear regression significance of 0.02, that should be 0 for like a perfect y equals mx plus b relationship, so it's pretty good. And then this is kind of a little point, but the images that were most memorized by group 2 were also these negative images, but this correlation didn't exist. So based on this fact, I predicted that the people, or we predicted that, the people with who saw the neutral and category images would also would not show the correlation like group 2 did. So we expect the negative people to have this positive correlation and the category neutral not to, and it turns out that was correct. The prediction was correct. They had correlation coefficients of 0.18 and 0.14, which is considered low, and higher linear regression significance, significantly higher. The maximum number this can be is 1, and we had 0.02 for the one before, so that's significant. But the problem is we don't know exactly what that means, other than the fact that that's never been seen before, and now we kind of got to figure out what to do with that. Yes.
Yeah, so basically just to wrap up what we did, just kind of a quick summary. We took the EEG that we recorded from the test on the subjects that we had come in, and we took those signals and used the Higuchi method to break them down into fractal dimension, which is something that we can look at and try to understand what it says about complexity, and then look for a link between that signal complexity and activity in the brain, specifically in our case, memory.
We're also hoping to connect our data with the heart data and seeing, because we have this down, theirs down, and we can see if there's any connections in the head and the heart, which was the ultimate goal.
All right, questions? In the back.
Was there did you guys get any evidence to support the idea that the reason why the negative impact, right? The ease of recall of negative images to fractal density was connected at all to the personal trauma of the participant in the study. Perhaps rather than simply noticing a negative image, there's also some sort of recollection of a personal.
Yeah, so we have the depression, like, what's the test called?
BAI and the BEI surveys.
So we have information on that. We haven't looked at that. Could be something to look at because we do have this positive correlation, and that could have something to do with it. And it's worth looking at, but that's not. We haven't found that yet, but it could be. Yeah.
Other questions? Yes.
So when you were picking which parts of each cap had the electrodes in, why did you do like an entire covering in the head and not looking at like specific memory pathways or areas of the brain? Like why?
So we can do that. Actually, the results we had were for the central electrode in the brain, but we're planning on doing for the frontal lobe, and beyond that, that's another thing we're probably next semester will do. Yeah, that's a good suggestion.
Anybody else? All right, thank you.